Logan Lott. Welcome to my new YouTube channel. Today we're going to be doing some physics, which is my favorite thing ever. I like it even more than chocolate milk. This is not a bit. This wasn't even on the script. I'm not kidding.
Hey guys, it's me, Noah Kuchek.
Let's get funky. Kinetic energy.
Hey Logan, what's the deal with kinetic energy? Do I have it? Do you have it? Does China have it?
Well, Noah, I can tell you the deal with kinetic energy. Kinetic energy is a form of energy which is the ability to do work or cause a change in a system. Specifically, kinetic energy is the energy caused by motion. In fact, we all have kinetic energy when we're moving.
Wowzers. So if there's a ball rolling over a surface, it has kinetic energy.
That's right.
And if I am running away from a horrifying creature, I have kinetic energy.
That's right, pal.
Now, perchance, what if I wanted to, say, calculate a body's kinetic energy with some sort of handy-dandy equation with letters and such? There wouldn't happen to be some simple yet effective equation for this.
Noah, there actually is an equation just like that, because of course there is. It's 2023. That equation would be K equals 1/2 mv squared.
So, if the m, mass, were to increase, kinetic energy would also increase?
Absolutely.
And the same if velocity increased?
You betcha.
Wow, that really butters my bread.
Ha 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 ha
Ha ha
ha
ha
ha
ha
ha
ha
ha.
ha.
Anyways, I'm gonna pass the mic over to my brother in Christ, Noah Kuchek.
Thank you. Now you're probably wondering, what is potential energy, and why is it so cool? Well, I'll tell you. Potential energy is stored energy that exists within an object because of its position or state.
Stored? How can energy be stored? Wowzers!
Shut up. I'm describing it right now. I was just getting to it. Alright, anyways, take springs. We all have springs, for example. When a spring is compressed, like so, it'll have more potential energy than when it's standing on its own. Once an object is in motion, potential energy is converted to kinetic energy. Do you get it now?
I think I'm starting to understand. So basically, you're saying that a force must act on an object for potential energy to be stored?
Well, I actually didn't say that, but we can go with that. It's true. So there's also an equation for potential energy of spring. Potential energy of a spring equals 1/2 kx squared. And this one's really going to blow your socks off, bub. The equation for potential energy itself is potential energy equals mass times gravity times height.
Holy guacamole! So potential energy is determined by its position and not its velocity like kinetic energy is. This is one of the equations of all time.
That's true. I am so very, very, very giddy because it's time for my favorite old thing, conservation of energy. I like conservation of energy even more than Logan likes a big old glass of chocolate milk.
That's true.
So, what if I told you that energy is always conserved? That is, it is never just created or destroyed. In fact, energy can only be transformed from one form to another, like potential energy to kinetic energy. For instance, let's look at mechanical energy in an isolated system with only conservative forces.
Is that like a mechanical pencil? Tee.
So mechanical energy is equal to the sum of kinetic and potential energy. Also, since energy is not created or destroyed, the initial mechanical energy will thus equal the final mechanical energy. Isn't that just splendid?
Sure is. Okay, let's get non-conservative for a second.
Yes! Finally!
Yep, non-conservative forces.
Oh.
You ever heard of friction, air resistance, or, dare I say it, tension? Well, that's what those are! Forces where work depends on the path taken by an object are non-conservative. They take energy away from the system as it progresses.
So, what about those, darn conservative forces? What's the deal with those?
Those are like the opposite. The work for a conservative force is the same for any path between 2 points. So you got your gravitational forces and spring forces. That's conservative, baby!
Holy crab! That's gosh diggity dope. Now, what if I wanted to know the value of the work of non-conservative forces? Would you let me in on that?
In that scenario, I would use the equation work non-conservative equals force non-conservative displacement cosine theta, which is also equal to mechanical final energy minus mechanical initial energy. Okay, let's just take all that and okay, anyways, an 80-kilogram skier starts from rest at a height h equals 30 meters above the end of a ski jump ramp and leaves at an angle of 32 degrees. Neglect air resistance and assume the ramp is frictionless. What is the maximum height h of his jump above the end of the ramp? And if he increased its weight by putting on a backpack, would h be greater, less, or the same? So we got this point, and then we got this point. Okay. And then we're going to have energy initial equals energy final. Wow, that looks bad. And at the initial point is only gravitational potential energy. Final point, we're going to have kinetic energy final. Yes. And gravitational potential energy is going to equal mgh, and kinetic energy is going to be 1/2 mv final squared. So the masses here cancel out in the equation. So we're left with 9.8, and then the height, which is 30 meters, that's going to equal 1/2 df squared. Okay, so you done plug that in, and you get velocity final equals 24.25 meters per second. Now you can use that in a kinematic equation, as you'll see here in a second. And we'll have vy squared equals the initial sine theta squared minus 2g change in y. Now plug in, it's going to be at this point, so the velocity is going to be 0, and the initial over here is going to be our final from before. It's going to be over here, 24.25 sine of our 32 degrees squared minus 2 9.8 change in y. Kind of running out of space here, but you add this to the other side, this part, 2 9.8 change in y equals 24.25 sine 32 degrees. Now you darn plug that in, and you get change in y equals 8.4 meters. And now it's going to be the maximum height, h. So h equals 8.4 meters. Now the question, if he increased his weight by putting on a backpack, would h be greater, less, or the same? Changing the mass isn't actually going to affect the height. So as you can see here, m cancels out, so it has no bearing on the final height or any other factors.
Alright, so imagine we have a block attached to a 1.2 meter string, like this. That's 1.2 meters. But the string, however, is pulled back to an angle of 50 degrees. We'll say that's like that. It's the angle. If it is released when it passes through the lowest point, which will be down here, a razor blade will cut the string along the block to slide across its surface, like so. It has a coefficient of friction of 0.387. How far from the point where the block starts sliding across the surface will the block stop? Like right here. So first we're going to want to find the velocity when it's right here. So we're going to use the potential energy up here is equal to the kinetic energy down here. So that's going to equal mass times gravity times height equals 1/2 mass velocity squared. So the masses will cancel out. We'll go to the gravity of 9.8 times the height, which in this case, since we have a string swinging, the height will not just be the length of the string. It's going to equal the length times 1 minus the cosine of the angle, which in this case is 50 theta. Alright, so times the 1.2 1 minus cosine of 50, and that is going to equal 1/2 times the velocity, which we are looking for, squared. Now when you go through, you multiply all this together, and then you divide by the 1/2, and then you take the square root of that. You find that the velocity is 2.9 meters per second. So now we're going to try and find how far it goes. We have the velocity right here, which is helpful. So we're going to use the work equals the change in mechanical energy, which will be F d cosine 180, because in this case the force that's being used is friction. It's going to go in the exact opposite direction of the block, so it's going to be 180 degrees. Now you're going to set that equal to the change in mechanical energy, which in this case is just going to be a negative 1/2 mass velocity, that's initial, squared, because we're going to start down here with just kinetic energy, and then when we land here there's no energy being used at all. There's no potential because it's right in the ground. It's going to equal 0. There's no kinetic energy since it's not moving. So when we subtract the initial over here from the final, this is all we have, just this kinetic energy. Now for the force, you're going to use force normal, which is going to be equal to the force weight. The equation for force normal is that U times mass times gravity. I'm going to make this all negative because of that cosine 180. It's going to be multiplied by that distance. Now we're going to have the negative 1/2 mass velocity initial squared. Masses will cancel out. Now we just have to plug in the negative 0.387 times 9.8 times the d, which we are looking for. It's going to equal negative 1/2 times the velocity initial, 2.9 squared. Now it's just simply solving. You multiply this side together, you're going to get negative 3.8 d equals that negative 4.205. There we go. Just do the math. The d, it's going to equal 1.11 meters.
Alrighty folks, wasn't that just a wonder, eh? Now Noah, why don't you give us a brief summary of our little lesson today?
So we talked about kinetic energy, which is energy caused by motion. We got our potential energy, which is caused by an object's position or state. There's conservation of energy, and there's non-conservative forces like friction.
Wow, look at all that physics. Wow, just wow. I hope you guys were as delighted as I was to have this nice chat about physics. Signing off. Logan Lot out.
See ya.